we want the dipole moment of this sphere, yeah? Well, we know that what's the dipole moment in general for a charge distribution, volume charge distribution. The dipole moment is r prime rho r prime d tau prime.
Yeah, you don't have the snowball with you, do you?
What's that?
You don't have the snowball?
Snowball?
Yeah, I hear all this other stuff. Like I hear the fan and I hear like this like slapping noise.
No, I think the reason you are hearing that is because I am not on combinations. So these, of course, are vectors here. Yeah. And we know in this question, keep in mind, we do have symmetry because we have a shell. So what we have a shell, yeah, and glued on this shell is some charge distribution. He's saying sigma 0 cosine theta. Okay? So we know we have symmetry, and we know that the dipole moment will point in the z direction. So we know that the dipole moment will be in this direction. Okay? Let's say this is P. So what we know for sure is P will be whatever, some magnitude of P, whatever P is, in the Z direction. Right? And how do I find P? Well, P then will just be, I'll give you more hints here, will be, just follow that. So if you're along the Z direction, then obviously R prime is Z. Yeah, R prime is Z, so becomes Z integral of Z rho d tau. Right? But this is a shell. This is a shell. So you know how to change this from volume integral to surface integral? Well, look, this is nothing but the total charge. This is the total charge. So if you need to switch this to a surface integral, you could then just say switch this to an area integral. Yeah?
Yeah.
An S. And what's the total charge for a surface? It's just sigma dA. You know, they all go hand in hand. If you remember when we from a previous chapter, when we did this before, these all go hand in hand. Lambda dl is the charge on a line
Yeah.
Okay, continuous distribution on a line, and then sigma dA is the amount of charge on a surface, and which is the same thing as tau rho, which is, so sigma is an area charge density, rho is a volume charge density d tau. So this is you know, for a volume of charge. Yeah. So if you were to integrate each one of them, you would recover the total charge found on a line on the first one, on a surface area on the second one, and in a volume on the third one. They all give you here, let me just since this is important, let's drag it down here. They all give you, right, they all give you Q total. let me write this appropriately. So Q total, if you have a line charge, is lambda dl. If you have an area charge, sigma dA, and if you have a volume charge, it's rho d tau. These all mean the same thing depending on what kind of surface what kind of charge we are dealing with. This is all for a continuous charge distribution, but whether that distribution is line, surface, or volume is what decides which one of these you use. Here, the shell, we have a surface of the shell, so we have to use the surface charge density to capture all the charge on the surface of the sphere, and that's sigma dA. Okay, so continuing on this here, I will get we have the charge density, which is, so P is equal to now Z is just R cosine theta, and we have sigma 0 cosine theta is the surface charge density, and then we have dA. Okay, now what is dA in spherical coordinates? Well, if we take, or sorry, in the if we take the piece of the shell, we know that we have it's let me do it here on the slide. So dA will be there's no R is constant, there's no R dependence here, so it's just dl phi dl theta. Okay, now dl phi will be R. We're on the surface of the sphere, we could just call this R. This is so let's see, if we take a slice of the sphere, so like this, and so this guy here, let's see, this guy here will be I mean, we know what it is. So let's see. If this is d theta, this would be R sine theta, and dl phi will be R sine phi or sine theta. So here we have d theta d phi. D theta d phi R. Wait, messed up. R sine theta till this pen writes, got stuck. So dA, let's do it here. So dA, here there is no R dependence. So this will be dl theta dl phi dl theta dl phi pointing in the R direction. And of course this is a vector. Okay, well, if we take a small piece, we know, like if I go behind this guy here, this is d phi. Let me draw this more clear. Right? If I were to take a piece of my area, and so this is just a piece, it's almost rectangular. So if so, this is the phi direction here. So this is d phi, and if I go up to here, so this here is different. This is d theta here. This is going down from the z-axis, which is the same. Yeah. So so this guy here is theta, and so we can see that this side here, this is 90 degrees. So this is r. So this will be r sine theta. So this piece here, so this is the area of this, so this will be r sine theta d phi, and then this piece here is just r sine theta d phi, right? And this is sorry, this is r, so this means this is theta, which would make this r sine theta, and we will get, so dA will be in that case, right, r sine theta. So this guy here will be this is a d theta, will be r, and that triangle will be r d theta. R d theta, r sine theta, r d theta. So we will get, when we multiply these two together, we will get r squared sine theta r squared sine theta d theta d phi. There's two r's and a sine, yeah, d theta d phi. And this is in the r direction, so yeah, r. Okay, so plugging this here, so this is since we're on the surface of the sphere, we could just plug in r squared sine theta d theta d phi. Phi is running us from 0 to 2 pi. Theta is running us from 0 to pi. The d, so let's pull all the constants out. So we have an r squared, so that's r cubed sigma 0. I have this guy will give me a 2 pi here, and we will get cosine squared theta sine theta d theta from 0 to pi. And
no,
so
I can't move it.
be, are you moving the
can
pad,
I
Ben?
do that?
Huh?
Okay.
You could, but let me, since I'm writing, let me just finish. Okay, so 0 to pi. And this is a straightforward integral u du. If u is cosine, du is minus sine d theta, so this becomes r cubed sigma 0 to pi. Now if theta is 0, u is 1, and if it's pi, this is minus 1, so we get u du, and there's a minus sign here, and so this becomes minus r cubed sigma 0 to pi u squared over 2 from 1 to minus 1. So what do we get here? R cubed sigma 0 to pi half wait, this is u squared. I messed up here. This is u squared, so this is u cubed over 3. So so this is 1/3 minus 1 minus 1, and there's a minus here. So the final answer will be P equals so minus minus cancel out, and we get what, 4/3 pi r cubed sigma 0. Anything else? 4/3 pi r cubed sigma 0, and then we have, and if this is a vector, we said that this is pointing in the z direction, so this would be the dipole moment. Yeah. Yeah, so next it's asking what's Q total. And that really should be a straightforward matter, yeah? I just showed you a moment ago how to find Q total on a surface area. It's just sigma dA on the surface.
Yeah.
Yeah, so we just integrate the surface charge density over the area, we find the total charge. You wanna attempt that? I'll do it here too. So let me roll through it. So Q total equals, okay, so this is a double integral, and what sigma is sigma 0 times cosine. Okay, so sigma 0 cosine, and dA, just like the previous question, we said it was r squared. We're on the surface of the sphere, so this can just be big R, because this is r. And then we said it was sine theta d phi. On phi we're going from 0 to 2 pi, and on theta we're going from 0 to pi. So if we bring the constants out, sigma 0 r squared, okay, this guy will give us a 2 pi, and the other guy will give us, well, as you might expect, a 0 here, because this is minus sine theta, or sorry, sine theta from 0 to pi. Sine pi is 0, and so is sine 0, so this guy is 0, so we get Q total equals 0.
Yeah, I treated that like U
Q
du, and
total equals 0. Wait, yeah, that I was wondering why we got. Oh, I forgot my sine term. Yeah,
I treated that like U du.
sine theta d theta. Wait. Yeah. So yeah, this is u du. So okay, wait, I forgot my sine term. I was wondering how could the total charge be 0 because we do have
Yeah.
a surface charge density. So this is sigma 0. Wait on this. R squared 2 pi. So if sine is u, cosine is du. So this will just be sine squared. Oh yeah, it's still 0 because yeah, it makes sense. Because you know, sine pi is 0 and sine 0 is 0. Let me think. Sine cosine 2 theta. What? Well, this is nothing but
Yeah.
if sine is u, okay, u squared over 2. Yeah, you get 0 because this guy goes to 0. Yeah, and even if you you know, if you wanted to do the shortcut and replace this with 1/2 cosine 2 theta, sorry, 1/2 sine 2 theta, the integral becomes cosine 2 theta. This is 1/2 sine 2 theta. This becomes cosine 4 theta over 2, which gets you 1 minus 1, which would get you 0 either way. Okay, so Q total is 0, yes. Yeah, so to find the potential, if you remember last time, let's not redo the derivation, but it's actually interesting because we did the derivation that this question asks for. If you remember last time, we did this derivation, we did the whole thing, you know, I showed it to you from scratch, and we got this formula for the potential, if you remember. So that includes all the terms in it: monopole, dipole, quadrupole, etc. So you know, he's asking you to redo this, but we've already done it, so let's not go back and redo it, right? Since have we not done it, he probably wants to see it, so you should do the same thing for the problem we are in.
Yeah.
You know, like arrive at this formula the way we did by the math, right? Starting from 0, like we did here, if you remember, on 326. So since we've already done it, if you want, we can just pick up the result here and just use it directly because we've already derived it, yeah? So let me copy and paste this down there. So let's see. Let's paste it here. Okay, so this is the result we got last time when we did the multiple expansion from scratch. And if I want to start with this, so the first one, if n is 0, I get the monopole term, yeah? If the first term is 0, so let's start with the monopole term. Let's see what that gets us. Well, what do you expect? I mean, I expect it to go to 0 because Q total is 0 and the monopole term is directly proportional to the total charge. So let's see. So this is 1 over 4 pi epsilon. If n is 0, so this is the monopole term is the first one. When n is 0, you get 1 over r, and if n is 0, this goes away. You get Legendre polynomial, the first one, right? What's the Legendre polynomial p0? That's just 1. Rho r prime d tau prime. But what's this? This guy here is the total charge. This is exactly what we found up there. right? Before the on the question before this one, we found the total charge. This turned out to be 0. So if this guy is 0, then the monopole term will go to 0. So V monopole equals 0. Yeah, there's no result from the monopole. Okay, let's go to the dipole term. So the dipole term, yeah, for the dipole we have what do we got? We got monopole term is 0, dipole term, so that's n equals 1. So plug in that formula we derived, so we get V for the dipole equals, let's copy here what we have. This is 1 over 4 pi epsilon, yeah, 1 over r, because and wait, 1 over r squared, because n is 1, and then we have the integral of r prime to the 1, yeah, and we've got Pn cosine theta prime, that's for n equals 1. So what's the first Legendre polynomial? That is cosine theta, I think. The first Legendre polynomial should be cosine, yeah? Just make sure here. Yeah, it's cosine theta prime, and now we have rho r prime d tau prime. Yeah. Okay, well, on the previous question, on the previous part before this one, we found out what the dipole moment is. It was this, correct? And we know, let me see how we're gonna fit this there. So yeah, so this one turned out to be r cosine theta. Okay, so that's the second term here. Yeah, that's when n equals 1. So you know what to do next, Ben? So I mean, here we could use a little bit of substitution just so we don't have to repeat what we did again, because we know that this guy here is nothing but theta is theta prime is the angle between r prime and r, just like we indicated on this previous problem. So r prime cosine theta prime is nothing but r dot r prime. Now, since this guy does not depend on the prime coordinates, I can put it outside. So then my V dipole becomes I can pull it outside the integral because the integration is with respect to the prime coordinates, not the unprimed coordinates. So this becomes 1 over r squared, and this is r hat here, right? Dotted with, I have to leave this guy inside the integral because it's primed. So this becomes r prime, right? Rho r prime d tau prime on V. Okay, notice this integral does not depend on r. And what did we call this? This is our dipole moment. We've already calculated that. We don't have to redo it again. This is P. Without this dot here. This is P. So that means my V dipole becomes 1 over 4 pi epsilon 1 over r squared, and then if I dot this, what did we get for the dipole moment? We got 4 pi. So this whole P turned out to be from the previous one 4 pi. No, not 4 pi. Oh yeah, it was 4 pi. Yeah, 4 pi r cubed times sigma 0 over 3, and that's in the z direction. Yeah. So there's no more integrals. We've already done it. That's why I wanted to replace it with the moment, with the dipole moment. Okay, so these guys go away. We get, what do we get here? Sigma 0 r cube over 3 epsilon. We have an r squared term. So as expected, the dipole moment is inversely proportional to the r squared term. And what is r dot z? R dot z is just cosine the angle, because it's the angle between them. Yeah? So r cross z is just cosine theta. So this is our dipole term. So this is the potential. This is the first non-zero term. We can continue on and find out the higher ones using the the general form of the potential. But the question said you could stop with the first leading non-zero term. The monopole was 0, the dipole was non-zero, so he just wants you to go up to the dipole term, but the remaining terms should be similar. You just take n equals 2 and move on to the second quadruple potential term. Now notice he in example 3.8 he did, in the book, he did find the exact potential of a sphere with a constant charge surface density. And if you look in equation 387, you will find out that his potential, the exact one, is our V dipole, is the potential that we got for the dipole term. Now, remember, this is exact. This is using, this is using the differential equation. This is using separation of variables when he got the generated polynomials. So equation 387 is the exact potential for this scenario, and it's identical to our V dipole. So now when he says, what does this tell you about the quadruple moment and higher order moments of the surface charge distribution? Well, if they all have to go away, they all have to be 0, because if V exact turned out to be V dipole, turns out to be equal to V dipole, that just means all the other multiple expansion approximations for V has to go to 0, which means we know V monopole goes to 0 because we did it, but that means V quadrupole and anything above it, octupole, so on and so forth, anywhere where n is greater than 0, 1, Anywhere where n is greater than 1, these all have to go to 0, and if they have to go to 0, then the dipole moments, the higher moments of the surface charge distribution has to go to 0. Right, because we in the exact potential we just pick up the dipole potential of this charge distribution. Nothing else shows up. So it must have been that they're all 0. Now we only did the monopole and we got 0, but you can easily go through the integrations, you know, and find out the higher order terms. But according to the fact that V exact turned out to equal V dipole, and the exact has to be exact, that means everything else has to be 0.